we did this find all the primitive solutions. So if you remember, this equation we are trying, right? A cube plus b cube equals to c square. So we found all the
Okay.
primitive solutions where the first two components are equal, right? So that is characterized by like this: 2n square, and 4n cube, right? So yes, the only one part is left. So they're asking that to find a primitive solution where a is the first component is strictly greater than 10,000. That is your party. So how will you do that?
Where A is greater than 10,000.
All right.
Mm, but where exactly are you going to put that restriction? Because A already is generic.
Yes. Right.
So, okay, he is asking for a specific kind of solution for specific numbers.
Right. So we have to find an example where I have a restriction with a is strictly greater than 10,000. Yes. Okay. So
So we
part.
can say that 2n to the square is greater than 10,000. We can start there.
Yes, that we can do. Yes, that we can do. Okay, so the primitive solution, the definition of primitive solution, what we said is that it does not look like this n square, n cube, right? So actually, we cannot use 2n square, 4n cube.
Oh, I see, I see, I see, I see. Yeah. That is not a primitive solution.
Right. Okay.
Mm-hmm.
So yes. Okay. So how should we do that?
Mm.
Okay. So one parameterization we had, right? So I think it is in right. So this parameterization we had, right? This ABC equals to x into x cube plus y cube and these things, right?
Okay.
Right. So if I take x equals to 1 to just to simplify the things, okay, let us use this parameterization.
But I thought that was just like a hint. It's not like a general parameterization. It was a hint
Yes,
that was.
that is yes, that is hint also, but this actually we got that this is a parameterization, right? Because this we proved, right? So for any so the condition what we had is, so suppose ABC is xz, yz, and z square. Then from the
Mm-hmm.
relation we are able to replace z by x and y, right? So now we
Mm-hmm.
have only two variables. So this was a parameterization, some sort of parameterization, right? So we have to find an example. So I think this will work. Okay.
Okay.
Right. So if I use this parameterization, okay. So to reduce, so here actually we have freedom to choose x and y. To reduce the number of variables, so if I take x equals to 1, then a equals to 1 plus y cube, b equals to y into 1 plus y cube, and c equals to 1 plus y cube whole square, right?
Okay.
Right.
Mm-hmm.
So now, if I want to make a strictly greater than 10,000, then what should I choose y? So let us see that. So we have 1 plus y cube strictly greater than 10,000,
Mm-hmm.
and so y cube must be greater than 9, right? So what is the cube root of 999? Does it exist? So let me check. right? So it is approximately, so y is greater than cube root of, right? So this is approximately 2.21.54 something. Okay. So if I take y that is greater than equals to 22, then our a is strictly greater than 10,000, right?
Mm-hmm.
Okay.
Yeah.
Right. So I think this will work. So if I take, suppose, in fact, we can choose y equals to 22. Then a will be 1 plus 22 cube.
Mm-hmm.
I think that will be 10649. And similarly, you can calculate b and thing. So 22 into 1 plus 22 cube, and c equals to 1 plus 22 cube whole square. So this is primitive because from here you are not getting any common n square term, right? So it is saying, right? So it is primitive. It does not look like this. So you cannot get a square term like this common out of 1 plus y cube, right? Because of the form of 1 plus y cube, right?
Mm-hmm.
So this is an example of a solution where it is a is strictly greater than 10,000, and it is, so this is the solution. Okay.
1 plus 2. And you just guess. I mean, you just guess like x could be 1, but
Right. So we can also take y to be 1 and something. So this is the smallest one what we can choose, right? X equal to 1, just we chose for, right? So we cannot, if we took x equals to 0, then it is not possible, because then the first term will become 0, but we
yeah.
require positive thing, right? So the x equals to 1 is the smallest one what I can choose, yes. But anyway, means the thing is, you have to find something that is the total a value is strictly greater than 10,000. So you can take any other value of x also. Accordingly, you have to choose y such that a crosses this mark. So that is the idea.
Mm-hmm.
Fine.
Yeah.
Okay. So now I think this ends the fourth one. So we'll move to the fifth one.
We move. So we find we finish
The
C.
fourth one, the fourth text. Now we are moving to chapter 5.
Ah, okay.
So it is about divisibility.
Yep.
Divisibility and GCD, the greatest common divisor. Okay.
So GCD is used everywhere. Like we have been using GCD all the time already.
Yes, yes. GCD, yes. GCD is also used everywhere. So I think here they are formally defining the term. Okay. So
Okay.
suppose the first definition is, so suppose m and n are integers, and n is not equals to 0, then we say that m divides n if n is a multiple of n. So this is obvious, right? So if there exists an integer k such that n equals to k times n, right? And will the notation will write is the notation for this is m divides n. Okay,
N divides M. M divides N. Okay.
right. And if m does not divide n, then the notation what we will use is this will give a cross to that line. Okay.
Okay.
Right. Yes. Now the greatest common divisor, the definition is mm, the greatest common divisor of A and B. So both not 0. Otherwise, it does not make sense. Is the largest number that divides both of them.
Yeah.
Right. So the notation is, we already know, it is GCD of A comma B. And particularly, if GCD of A comma B is equals to 1, then we'll say that A and B are relatively prime.
Yeah.
Fine.
Mhm.
I think this is okay. So this is the greatest common divisor, and this is the relatively prime. Okay. So for example, just to get hands on to it, so what will be the GCD of 12 and 20?
4.
4, right? Yes.
Yeah.
Okay. And suppose you have a slightly bigger number. So for example, 225 and 120.
Maybe 5 or
More than 5. So we'll have something else.
25.
25 you're saying? 25, I think
Oh
120
wait,
is not divisible by 25.
15.
15. So the thing is 15, right? So if you have smaller numbers, so actually we can use something called the prime factorization, right? So 225 is nothing but 3 square times 5 square, and 120 is nothing but 2 cube times 3 times 5. Right? So the common thing what you can see is there is 1 3 here and 1 5 here. So the GCD will be 3 into 5, right?
Yep.
Right. So this is fine. But the thing is always prime factorization, finding prime factorization is so if you have a calculator, that is fine, but just finding prime factorization is always not efficient. So sometimes there is another method to find the GCD, that is the Euclidean algorithm.
Sorry, can you repeat that?
Euclidean algorithm.
Okay.
So this is the most efficient method to find GCD of two numbers. So we'll see how the algorithm goes for a smaller numbers, and then we can try for something else. So suppose you want to compute the GCD of 36 and 132. Okay. So yes. So what we'll write is, so we'll express 132. We'll divide by 36 and write in a form of quotient and remainder. So suppose I want to divide m with n, right? And suppose it is not exactly divisible, so I write is n times q plus r. So this is the form, right? This is the quotient, and this is the remainder, right? So we'll use that form. So 132, it's 3 times 36 plus 4, sorry, 24. Okay.
Okay. Yeah.
So now the next step is I will bring this 36 and divide it by 24. So 36 I bring here. So this is 1 times 24 plus 12. And then I divide 24. So 24 is 2 times 12 plus 0. So when our remainder is 0, we'll stop that step. Okay. We'll stop at that
Yeah.
step where our remainder is 0. And the previous remainder will be our GCD. just before that.
Yeah.
So this is the
Mm-hmm.
GCD of 36 and 12, 132.
Right. Yes, that's according to the Euclidean.
Right. This is a Euclidean algorithm.
Mm-hmm.
So yes. So let us try for another example. Then it will be more clear. So we already found out 225 and 120. So let us use Euclidean algorithm to check how it is coming.
Mm-hmm.
So yes, you tell the steps. So GCD of 125 and 1, how much? Sorry, 225 and 120.
Okay, so 25 would be
Right.
would be 1 multiply 120
Yes, yes. So it will be 1 multiplied by 120 plus remainder
plus
is
105.
right. Next step will be
120 equal to
right.
120 would be equal to 11 multiplied by
No, you are dividing
5.
by 105, right?
Oh yeah, 101.
So 1
Oh,
times it.
again 1.
Remainder will be 15.
Yes, 105 plus 15. Right, then the next one would be 105 equal equal 7.
Right.
7 multiplied
So
15.
right. So we have
That's
ended
0.
here. So this is our GCD.
15.
Okay.
So the quotient will be always
Yes.
the
So we
smaller
start with
number.
yes, we start with a bigger number. We divide with the smaller number. Now this number goes here. The remainders come here. This number goes here. The remainder come here. So this is the step.
So I meant the divisor. So the divisor 117 will be always the the smaller between the divisor and the quotient, right?
Yes, quotient will not compare with. Quotient we are not taking into consideration. We are considering only the divisor and the remainder. So remainder is always strictly less than the divisor, right? That is by definition, right?
Mm-hmm.
So m equals
Yeah.
to nq plus r. Then this r is always less than we are dividing by n, right?
Mm-hmm.
Right. So that
Yeah.
is the thing. So that's why we will
Yes.
again go to the next step, right?
Mm-hmm.
So in the book they have given an example. After that you can see that they have computed a very big large number. So for example GCD of 1160 718 174. So for example for this number trying to find a prime factorization it will be difficult because we don't know. The prime factors can be very big. So in this case since both of the numbers are big, we will prefer to use the Euclidean algorithm, right? So you can see the table on the next page. So yes, go check it once. I am not writing it down, so it's too much,
So
too big.
the prime factorization is only the divisors
Right, prime
elevated
factorization is
to anything.
yes, yes. So every number, suppose you have a capital N is a natural number, so you can write it as some p1 to the power alpha 1, right? P2 to the power alpha 2 like this. Suppose pk
Mm-hmm.
to the power alpha k. So here p1, p2, pk. So these are all prime numbers, and we have the exponents alpha 1, right? So this is the prime
Mm-hmm.
factorization. So this exists for every number. But the thing is, if we have smaller primes like 2, 5, 7, then it is fine up to 11. But if the prime numbers itself gets bigger, it is difficult to find just by with hand your prime factorization. So the Euclidean algorithm is always the efficient method to find the GCD. Right?
Mhm.
Yes, so you can see the table in the next place, in the next page. Right. So
Yep.
that is fine, right?
Yep.
Okay, so the GCD here they have obtained is 1078, right?
Yes. 107.
Fine.
Yes, it's fine.
Right. Okay, so if you go down, they have just described the algorithm in the next page. I think that is fine. Okay.
Yeah.
Okay, I think here nothing more is there. We can directly go to the theorem. Let us at least see the theorem. So that is on page 34.
The exercises. Oh, the theorem. Okay.
Yes, yes. So just the statement, a formal statement. Right. So it says, so suppose to compute the greatest common divisor of two numbers, so compute the GCD of a comma b. So we let r minus 1 to be a and r0 to be b. So these are the two things. And we compute the successive quotient and remainders.
What does it say equal to a
R minus 1.
r minus 1?
Right, right. Yes, I will explain you what you're doing. So on quotient and reminders. Right. So we compute r I minus 1 is equals to q I plus 1 times ri plus ri plus 1. So this is the step we do for every I equals to 0, 1, 2 and so on until some remainder rn plus 1 is equals to 0. So this is where we stop. And the last non-zero divisor is that is Rn is equals to the GCD of a comma b. So what they're telling is, so if I put I equals to 0, then I have the first step is, okay, so this is the theorem. So that is fine. Now let me explain. So r minus 1 equals to q1 times r0 plus r1, right? If I put I equals to, this is the
Equals to
first step,
0.
I equals to 0, right?
Mm-hmm.
But we have taken r minus 1 to be a, so this is a, and r0 to be b, right?
Right.
So this is my first step, right? The next step is I equals to 1. So here what I do is, so it becomes r0 equals to q2 times r1 plus r2, right? So that is what I told. So this r0 comes here, this r1 comes here.
Mm-hmm.
The next step is I equals to 2, suppose. Then I have r1 q3 r2 plus r3, like so. Here this r1 comes here, this r2 comes here, right? And so on we continue. At some stage I equals to n, and then what I have is r n minus 1 is equals to Qn plus 1 times Rn plus Rn plus 1, right? So if this is equals to 0, then we go to the previous step. So that is I n minus 1. So here there will be Rn, right? So it will be Qn times R n minus 1, and this is equals to R n minus 2, right? So here we will continue like this, right? So if this is 0, then this is our GCD of AB. So right. So this is the Euclidean algorithm, right? See the statement.
Yeah.
Fine, right?
Yeah.
Right. So I think this is it for this chapter. We can directly go to the exercises. So the first exercise, they are asking to compute the GCD. So there are 2 parts. Let us do at least 1 part for practice. Right. So we have to compute GCD of 1, 2, 3, 4, 5, and 6, 7, 8, 9, 0. Yes. Tell me what will be the steps.
It should be the other way, right? So 67.
Yes. Bigger number you have to take.
Okay. Oh yeah. Okay, so that would be equal to 5 multiplied by 1, 2, 3, 4, 5.
Okay.
Plus 61, 65.
Right. 61, 65.
And then 1, 2, 3, 4, 5 is going to be equal to 61, 65, right?
Yes. How many times?
2?
2 times, right. What is the remainder?
15.
15.
And then 61, 65 divided by 15, right?
Yes.
By 15. 411.
Right.
And the remainder 0.
Right. So we'll stop here, and this is the GCD.
Right.
Okay. So, right. Let us see. What do we have? Yes. So next, the second part, that is fine. Similar thing. So question 2 is they are telling you to write some program that maybe you can do later on, right? To find the GCD of A and B. So you have to input. So you have to write a program such that if you input 2 integers A and B, the program should run and give you output as the GCD of A and B. So I think that you can do, right? That is not a big deal.
So
Fine.
if one of those, if one of A or B is 0,
Right.
so there is no GCD.
Right. GCD is not. So in that case, that your program should show that the GCD is not valid because one of them is 0. So that result should also come. So you have to some loop. You have to run, right? If then statement or something you have to run.
Yeah. I got that. Yep.
That is fine. That you can do later. Okay. So let us let us see question 3. What they're saying. Okay. So question 3, they are saying that let B equals to R0, R1, R2, and so on. So be the successive reminders in the Euclidean algorithm, right?
Successive reminder, right?
In the Euclidean algorithm after applying to B and A and B. Right. So B equals to R0 means the first stage is B. The first stage is B, right?
Sorry?
So yes, let me show you. Yes. So B we are taking as R0, right? This is the how we define the Euclidean algorithm, right?
Yes, B
Right.
is R0, okay.
Right. So and R1, R2, R3, and so on are the successive reminders. That is what they are saying. Okay. In the Euclidean algorithm applied to A and B. Right. So now they are saying that show that after every two step, the remainder is reduced by at least half. So after every two step, the remainder reduced by at least one. So what is they're saying is Ri plus 2 is strictly less than half of Ri. So this is what you have to show. So at least it will reduce by half. So this is the thing that you have to show. So how to show that? So the question is clear, right?
Yes, so after you go down, like at every line,
Right.
after two
Yes.
times, the remainder becomes less than the half.
Right. Right. So for example, this is R1 and this is R3, right? So this is the after two steps of R1. So we'll see that this R3 is strictly less than half of R2, R1. So that is the idea. So similarly, it will go down like this. So in some sense, these reminders are in a decreasing order, right? Is a decreasing, right?
Yes, it will be always lower and lower.
Right. Yes. So yes.
Interesting. Like maybe we find a equation where we have Ri and Ri plus 2.
Okay. Then.
And then, I mean, maybe we can compare them or add anything to each side. I'm not sure.
Okay.
Or maybe we can start from there. Like if we already have the conclusion, Ri plus 2, can we go from Ri plus 2 to Ri on the left,
Okay.
and then we find out whether that is less than Ri over 2.
Right.
I mean, mm, so let's replace Ri plus 2 in the general formula.
Right. Okay. So the thing is, yes, we always know that the arrays are decreasing, right? That much we know. This sequence of reminders that are decreasing, right?
Yeah.
So it is clear that these arrays are decreasing, right? So now, if I know that there can be two cases, that Ri plus 1 is less than half Ri, right?
I plus 1.
Or so just if I compare the consecutive step, means I compare Ri and Ri plus 1, or it can be greater than Ri, right? Half of Ri. So these two cases can
But wait,
happen, right?
so I know it is less than, but why? How do you know it is already half of that?
No, no, no. Yes. So what I'm saying is this much I know, right? So these are decreasing. This the sequence. So what I'm saying is yes. So the sequence of Ri's, these are decreasing. I know, right?
Yes, that is correct. Yes.
Right. Now suppose I compare any two consecutive step. Suppose this
Mhm.
is Ri and this is Ri plus 1, right?
Mhm.
Right. So there can be only two cases, right? That is either Ri plus 1 is less than half of Ri, or it is more than half of Ri.
Oh, I see. I see. Okay.
So I am
You're
considering
saying
both of them, right?
both of them. Okay.
Right. Now, suppose this one is true, right? Ri plus 1 is less than half of Ri. Then since it is
Mhm.
decreasing, I know that Ri plus 2 is less than Ri plus 1, right? And it is further less than half of Ri. So then we are done, right? Because I have to prove that Ri plus 2 is less than half of Ri,
Okay.
right? So the only thing, the only case that you have to consider is that when Ri plus 1 is greater than half of Ri. So this case we have to see how to prove it,
Uh-huh.
right?
All right. And the right one.
So if I have this case, then we are already done, right? Then it is automatically true
Mhm.
because the sequence of Ri's are decreasing.
Yeah.
Fine. So we'll only consider the case. So suppose we can assume that Ri plus 1 is greater than half of Ri. So we'll consider this case,
Okay. The second case. Okay.
right? So now I know that Ri plus 1 is less than Ri. So that I know because the sequence is decreasing, right?
Mhm.
Mm, okay. Then when I divide this Ri by Ri plus 1, right? So what
No,
happens
you
is,
can divide
right. So what I
both.
can write this as like this, Ri plus 1 plus Ri minus Ri plus 1, right? So this is my reminder. This I can do it, right?
Wait. This is your reminder.
Yes, that I'll explain. So what I'm doing is, so from this expression, what I have is 2 times of Ri plus 1. It is greater than Ri, right?
Yeah. Okay.
And so combining these two. So if I combine this expression and this expression, so if I combine these two, then what I get is that Ri plus 1, it is less than Ri, and it is less than
Uh-huh.
2 times of Ri plus 1, right?
Okay. Yep.
So when I divide with Ri plus 1, it will only go one time, right? So it is only one times the thing, right? Because if I cover twice of that, then it will cross Ri.
Sorry, the last part I didn't get it.
Yes. So this inequality, up to this inequality is fine, right?
Yeah,
Right.
until there is good.
So now I want to divide Ri by Ri plus 1.
Okay.
So how many times Ri plus 1 will go? So it will go only one time, right? If I do two times, then it will cross Ri.
If you go 2 times,
Yes, it will cross Ri.
it will be lower, or sorry, what do you say?
No, it will overcome, means it will cross. It will cross Ri. It will be bigger than Ri.
If you go 2 times,
Right.
why?
Okay, let me tell you one thing. So suppose I am trying to divide n with m, right? So then what I write? M equals to nq plus r, right?
Plus
This is my
R, yes.
quotient and this is my remainder, right?
Right.
So the thing is, so it is going q times, means n lies between nq and q plus 1 n, right? Because
And Q. Right.
because r is strictly less than this divisor, right?
R is less than Q.
No, not q, n is the divisor,
N. Okay, R as less than N. Okay.
right? So okay, let me give you
Mhm.
a concrete example. So suppose 7 is there, right? And I want to divide it by 2. So what do I write? So 7 is 3 times 2, suppose, plus, okay, I'm writing nq. So 2 times 3, suppose 2 times 3 plus 1, right? So 7 lies between 2 times 3 and 4 and 2 times 4, right?
So
So this,
N is 2 and Q is 3.
right. N is 2 and q is 3. This is 1.
Okay, and you're saying 7 would be 2 times 3 or 2 times 4. Okay. Yeah.
Fine.
Yes.
So this, when I write in this quotient and remainder form, so this is the highest number that times n will go, right? Because if I do q plus 1, then it will cross m. It will become more than
Yeah.
m, right?
Mm-hmm.
So that is what I am saying here, right? So if I want to divide by ri plus 1, and if I do twice of ri plus 1, then it will crossing ri. So the highest term that will go here is 1 times this thing, right?
2 Ri plus 1. So you're saying if you divide by Ri plus 1,
Right. So I want to find ri equals to, this is the quotient times the divisor plus remainder. So what will be q? That is what I'm asking.
okay, Q will be Q the value of Q.
Yes, q, it has to be 1, right? Q cannot be 2, because if I write 2, then it is more than ri.
Q needs to be 1, you're saying.
Yes.
Because if it is if Q is more, you will pass to Ri plus 1. Ri. Mm, but that last R, I mean,
Yes, tell.
so okay, so you're saying okay. So what I understand is
Yes,
Ri would be greater than Q multiplied by Ri plus 1 and less than
q
Q
plus
plus
1.
1
Hmm.
multiply Ri plus 1. Okay.
Right. Then what is the value of q? So it follows from this inequality, right?
So you're saying it should match that inequality. That's how you derive Q.
Right. So it should match the inequality, right? Because yes, so from the this relation, what I have is q times ri plus 1, it is less than ri, and if I do q plus 1, then it will cross, it will overcome this ri, right?
Uh, Wait,
Yes.
but so that inequality it is something that we want to prove, right?
No, this inequality we have assumed. So this is the suppose, right? We have assumed this case.
You're assuming that is true.
Right, this is true, and also we know that since Ri's are decreasing, this also I know. So these two things I already know.
Okay, so that's why you are taking that as fact and saying Q cannot be, Q should be 1.
Right, Q has to be 1.
Q must be 1 to satisfy that inequality.
Right.
Let's see. So Ri will be greater than. Yes, I mean, if you have Q as 1, you have the same inequality as above.
Right. Okay.
Yeah.
So this forces, so this implies that Q has to be 1, right? So if Q is 1, then what is our remainder? So then I have Ri equals to 1 times
Ri plus 1.
Ri plus 1 plus this remainder, right? So our remainder is nothing but Ri minus
Ri minus 1.
Right. So this is what I wrote here. Okay. So this is our expression. So what I got is Ri equals to Ri. Let me write down 1 times Ri plus 1 plus this is the remainder. Right.
So below is the general formula, right? You're saying Ri is going to be a Q multiplied by Ri plus 1 plus some R. And
Right.
that R, we already found that.
Right.
Okay.
So, okay. So this is which stage? So if I go to the general formula, yes. Yes. So this is when I have I plus I minus 1, my remainder is I plus 1. So this is 2 steps different, right?
I see, yeah.
So here I have here I have I, here it is I plus 1. So this remainder is nothing but my Ri plus 2 in the Euclidean algorithm, right?
That should be Ri plus 2, right?
Right.
Yes.
So our remainder is so Ri plus 2 is nothing but Ri minus Ri plus 1, right? And
yeah.
Right. So also we are taking the case that, so this is important actually. So we are taking the case that Ri plus 1 is strictly greater than half of Ri, right? So now if I use that and Ri plus 1 is strictly greater than half of Ri, right? So okay. So now if I if you know, I think you know this. So when I apply negative sign, then the inequality changes, right?
Yeah.
Right. So from here it implies this thing. Now if I add Ri to both sides,
Ri, right.
so this is less than minus half of Ri.
Right.
So this is nothing but half of Ri, right? But this is nothing but Ri plus 2. So this is less than half of Ri. So this is what you wanted to prove. So this is the thing that you wanted to prove, right?
Yes.
Yes. So yes. So that you got, right?
Wait, so Ri minus Ri over 2 is equal to Ri over 2? I mean, where is that?
Yes, which one?
The below,
This
the
one?
line before the last one.
This one?
No.
Then?
Above the answer, it says,
Yes, this one.
yeah, that line.
Yes,
Ri
yes.
minus half of Ri is equal to half of Ri. Oh, because they are the same
Yes,
factor. Okay. And then on the left, you have Ri minus Ri plus 1. How come that is Ri plus 2?
Yes, this is what we found out, right? This is what we found out, right? Ri plus 2 is nothing but Ri minus Ri minus Ri plus.
Okay, we found that. So, okay, now we arrive to that conclusion. Okay, Ri plus 2 less than half of Ri. Okay, and we wanted to prove that.
Yes, that is that is what we wanted to show, right? So yes, so this is what, right? So after every 2 steps, it is reduced by half. So this is what we wanted to prove, right?
Ri plus 2 less than Ri. So scroll up.
Yes.
Ri plus 2 less than Ri. But okay, but how come both suppositions are correct? Because we will suppose the other way around, right?
No, I did not get you. Tell again.
So scroll up.
Yes, yes.
So you're saying so we suppose that Ri plus 1 it's either less than half of Ri
Right.
or Ri plus 1 is greater than.
Right. These are the 2 cases what we divided the care.
Yeah, but in those 2 cases it worked. In
Yes,
the
both of
second
them it
case,
worked, right?
okay, so but how come it shouldn't work? It shouldn't
No,
work
no.
both, right?
Yes, it should work for both of them, right? Because the thing is, the relation what you have to show is between I plus 2 and I, right? But here, what I'm assuming between I plus 1 and I, right? So there is not a contradiction, right?
No, but on the right of that it says Ri plus 1 is greater than half
Yes,
of Ri.
yes. That is
They
fine.
are
But
opposite.
any one of them can happen, right? So I proved it individually, right? So either of these 2 cases can happen, right?
Oh, okay. So it's not a contradiction. You're
Yes,
saying
that is
both
not
are
a
possible.
yes, both are possible, and I proved for both of
Okay.
them.
Okay. Yeah. Okay, I understand. Both are possible. Okay.
Right. So for this case, it is easier because Ri plus 1 if it is less than half of Ri, and I know that Ri plus 2 is less than Ri, so I can combine these two and get this one easily. So the only
Right.
case that I have to do work is when Ri plus 1 is greater than half of Ri. So then I have to do some work and adjustment to make it this thing.
I see. Okay. All right. Yes, I got it.
Right. So there is, I think, one more part to the same question. So they are saying that conclude that the Euclidean algorithm terminates in at most 2 log 2b steps, where log 2 is that is logarithm base 2.
Mm-hmm.
So yes, so that is the idea. So what b we know, b is the among a and b is the smaller quantity, and yes, b is the first remainder. B is equals to r0, that you know. So yes, so they are claiming that it terminates in log 2 steps, right? So I think that is also clear, right? Because the thing is, at every 2 steps, my remainder is getting less than half of the previous one, right?
Uh-huh.
So the sequence of remainder is drastically reducing, right?
By half every 2 steps, less than a
Right,
half.
right. So what you can say is, one observation is, after 2n steps, suppose we are computing 2n capital 2n steps, the remainder has been cut, so by at least a factor of 1 by 2 power n, right? Because there are 2n steps, so it has to be it is at least a factor of 1 by 2 power n, right?
Sorry. I don't understand that part.
Okay,
1 over 2
let me tell
to
you.
the n.
Right, let me tell you. So R1 I have So suppose I have this sequence R1, R2, R3, and so on. I am going. Okay, let me write down few more steps. R4, R5, R6. So suppose we have 6 steps, right? So now in the
Okay.
previous what you showed, I have showed that R3 is less than half R1, right?
Right.
Then I showed that R4 is less than half R2, right?
Yes.
And what I've showed is R6 is less than half
R4.
R4, right?
Yeah.
Right. So now this R6, now I can replace this R4, right? So here we have R0 also. So R2 is less than half R0. So now from here I can replace R4. So R6 is less than half. R4 is less than half into half R2, right? And which is further less than half into half into. Now I can replace R2 by half R0, right? So what I have is R6 is less than 1 by 2 cube R0, right?
So you're multiplying R6, R4. Oh, okay. I see.
Right. So here if it is 2n, so it is, you can see that is 2, the now number term is 2n, right? And it will be n. So it is less than a factor of 1 by 2 power n. So that is the idea.
So 6 is n?
Yes, suppose 6 is suppose after doing 6 steps our process terminates. So then our 6 is 2n, right? So for this example,
Sorry.
right? So n is 3, right? So that is
6
what I'm
is
saying, right?
2n.
So it will be less than 1 by 2 power n. So it will be less than the factor of 1 by 2 power n. So here is 1 by 2 cube.
Okay, now I get it. Okay, so 6 is equal to 2n. So n would be 3. So the total steps would be n, right?
Right. Total steps is 2n, not n.
2n, okay.
Right. So because we are comparing every alternative term, right? We are comparing I plus 2 with I. So that's why it will the power will be half the number of steps. So that's why 2n and the power will be 1 by 2 power n. So up to this part you understood, right?
Yeah, until now, yeah.
Yes. So I think it will take some time. So maybe we'll continue in the next class. Okay.
So from there we will find out how to get to logarithm.
Yes.
Of
From
2.
From here you have to find how to find the log thing.
Okay, thank you.